Okay, if we have, and let's see if we've actually posed this problem. Z equals 1 minus r squared, and we want the area, or the volume, beneath this graph lying above this curve, or this region, above the previous region. And we'll specify that the region 0 less than or equal to theta less than or equal to pi, 0 less than or equal to r less than or equal to sine theta. Okay, same region we had here. I haven't drawn that region down here. All I've drawn is, first of all, the typical interval, the delta r by delta theta interval, which has area delta A, the area contribution, and it's r star delta r times delta theta for the same reason that was the area over here. Now we also have z equals 1 minus r squared. For this region, we're going to calculate everything based on the sample point r star theta star, so that the z value of the function above this region is 1 minus r star squared. Well, that's going to be how far you've got to go from the xy plane down here up to the graph of this function z equals 1 minus r squared. Okay, now ignore the yellow thing here. We'll talk about that in a minute. What's the volume of this figure here? Okay, well, its base has this area. Its base is approximately rectangular. If you have very small delta theta, it's very close to rectangular. But it doesn't matter. If we take the area of the base and multiply by the altitude, which is our z-coordinate, we're going to get a volume. And that's going to be the volume beneath the 1 minus r squared surface above this increment. So our volume contribution is just 1 minus r star squared, the z-coordinate, times the area of the base. That's area of the base here, altitude here. And maybe that's worth actually writing down. Area of the base times altitude is your volume. Now we just sum that. We partition our theta interval. We partition for each theta interval. We partition our r interval the same way we did here. It's identical, except that now we're not calculating just area as we did here. We're calculating volume. And we arrange our r's and delta thetas and so forth, so that everything depends on r is here inside this set of parentheses. And the parentheses are correct, but let's emphasize this set of parentheses gives us our r dependence. And then outside that we have our theta dependence. Taking the limit in the usual manner, we have the same limits on our integral. For any theta, r goes from 0 to sine theta. No matter what theta is, r goes from 0 up to sine theta. And our thetas go from 0 to pi, so here's our integral. And that integral is going to give us the volume of the region between this curve down in the xy plane, and that curve would be like here in the xy plane, circle, and below the graph of z equals 1 minus r squared. Okay, now the graph of z equals 1 minus r squared is actually a fairly straightforward thing. It's nothing but a sphere of radius 1. Okay. Actually be a hemisphere, the upper half of the sphere. So this integral will give you that volume. Okay, I don't want to say any more about that. Now, we can also treat this region as a volume integral. And in the next video we'll do that. And in that video then we'll want a typical volume increment, which will be this yellow thing. It lies right above our delta R by delta theta increment, but it's also got a delta Z, so it's like a little box of dimensions R star delta R times delta theta times delta Z. It's going to have a sample point with coordinates R star, theta star, Z star. We'll see what we can do with that breakdown. It isn't necessary to do that breakdown to find the volume of this region, but for example, if we have varying density and we want to find the mass of the region, we're going to have to take into account how the density varies with respect to Z, and we're going to need this little box.